Okay, so next up is section 7.5, Propositional Theorem Proving. So let's dig in. Now, we can perform entailment by doing theorem proving, right? Theorem proving. So what this just means is that we're going to have some inference rules we'll look at, and we'll be able to use those inference rules with the sentences in the knowledge base to make a proof, right? And so by doing this, we can forego using models. You don't need to have any models for this, which can lead to a solution that's a lot more efficient. So to be able to do theorem proving, we need to understand what logical equivalence is, we need to know what validity is, and we need to know what satisfiability is. Okay, so here's your first definition, right? So you can say that if you have two sentences, alpha and beta, you can say they're logically equivalent if they are true in the same set of models. So we can write that as, what you see here, this little three bars or these three lines right on top of each other, right? That means logical equivalence. So A is logically equivalent to B, or alpha is logically equivalent to beta, if I was going to write that in Greek, right? So another example of this is, for example, P and Q, right? Well, P and Q is logically equivalent to Q and P, right? If in the first example, right, in this first sentence, if P is true and Q is true, then the whole thing is true. Now, for the second sentence, that's going to hold also. If Q is true and P is true, the whole thing's true. So alternatively, you can say that, two sentences, A and B, or alpha and beta, or P and Q, are equivalent only if they entail one another, right? So that's what this definition here is saying. So A is logically equivalent to B, sentence A is logically equivalent to B if and only if A entails B and B entails A. All right, so what I have here for you is figure 7.11 from the textbook, and this is a list of all of the standard logical equivalences, right? So if you built a truth table for this, if you went through, you could show that these guys are all equivalent to each other, and we're going to be using this table quite a bit through this entire section. A sentence is valid, right? Sentence is valid if it's true in all models, right? So if you've got, if you went through and you did have a truth table and you did enumerate all the possible models, right? That sentence is valid if it's true in all of the models that you went through and enumerated, right? So in all possible worlds, that sentence would have to be true in order for it to be valid. So here's a simple example, which is known as a tautology. P and not P, that's universally true, or excuse me, P or not P. That's universally true no matter what. I mean, in any model, any world, anywhere. Because if P is true, then the whole thing is true, right? Because you only need one of these sentences to be true for the entire disjunction to be true. Okay, so if P is true, then the whole thing's true. But what if P was false? Well, then not P would be true. So this thing would be true all the time, everywhere, no matter what. So this sentence is going to be valid. Okay, it's known as a tautology. It's necessarily true. There's no way it can be false. Now, let's see here. So a sentence that's true in all models, it's logically equivalent to true. From our definition of entailment, that allows for deriving this thing called the deduction theorem. Okay, and the deduction theorem was known to the ancient Greeks. It's been around for like centuries. And that just says that for any sentence, for any two sentences, alpha and beta, or as I have written on the slide here, A and B, okay, A is going to entail B if and only if the sentence, it shouldn't be seen tense, it should be sentence, if the sentence A implies B is valid. Okay, so that's the deduction theorem, and what that does for us is that sets it up so that A entailing B can be decided, right? We can decide that by checking if A implying B is true in every single model, right? Or if you can prove that A implies B is equivalent to true, right? So if you can do either of those two things, then you can verify that A entails B, right? So if in every model, in every possible world, if A implies B, then that means that A entails B, okay? Or if you can prove that A implies B is logically equivalent to true, then that would mean that B is entailed by A. So what that basically means, therefore, every valid implication sentence describes a legitimate inference. Okay, got another definition for you. A sentence is satisfiable if it is true in some model. Okay, so if it's true in some model. So you think about that truth table, right? If one of those rows you have a sentence and it's true, then that sentence is satisfiable, right? You can say that that sentence is satisfiable. Now recall earlier from the example where we were putting together, where we had a knowledge base where we were trying to put together a truth table to determine, if there was a pit nearby, right? And so we had these rules, R1 and R2 and R3 and R4 and R5. Okay, we had those facts that are part of our knowledge base. And all of these guys combined together, right, there was at least one row in that truth table we looked at in the previous video where this was true. Okay, so as it turns out, there were 3 models total. So that means that this sentence is satisfiable because in 3 of those models it was true. Okay, so how can you check if something's satisfiable? Right, if some sentence is satisfiable, enumerate all those possible models until you find one that satisfies the sentence. In other words, until you find one model where that sentence is true. Now, validity and satisfiability, they're connected to each other. They're connected, right? So, think of it this way. If you have some sentence A, right, that thing is going to be valid if and only if not A is unsatisfiable. That means is that A is valid only if not A is never true in all the possible models. Okay, and another thing to think about here is that A is going to be satisfiable if and only if not A is not valid, right? So it works in both directions. This leads us to, or allows us to derive or infer that B is entailed by A if and only if the sentence A and not B is unsatisfiable. Okay, so what does this mean? Okay, what this means is that you can prove sentence B by checking the unsatisfiability of A. Now, sounds really convoluted, but all this means is if you want to prove a sentence, you do proof by contradiction. Okay, so let's talk about inference and proofs. What you do to do a proof, use these things called inference rules, and you apply them over and over and over again to come up with your proof. Okay, so a proof is basically just a chain of conclusions, a bunch of conclusions chained together that lead to some goal. Okay, so what's the goal? The goal is that sentence that you're trying to prove, right? So you start off with some starting sentence, you apply a bunch of inference rules from that starting point until hopefully it leads you to a sentence that is your goal, right? So, for example, if you wanted to prove there's no pit in square 2, 3, right? You're going to start off with a basic set of knowledge in your knowledge base, which are a bunch of sentences or one giant long sentence, right? And you can apply these inference rules over and over and over again to the original starting sentence, and it's going to take you somewhere. You're going to go through a series of transformations. The sentence you start with is going to be transformed after you continuously apply these inference rules, and hopefully, eventually, the final transformation is your goal sentence. And if it is, then you've proven what you tried to prove. Okay? So, the best known inference rule, it's called Modus Ponens. So, here's how it's written. And what this just means is, if you've been given A, right, given A, assuming that's true, then you can infer B, right? So this is the implication statement, A implies B. If A is true, if you've been given that, then it's safe to go ahead and infer that B follows from A, right? Let's say that A was, here, I'll do it on both sides here. So let's say this was our A. Okay, that's our A. Wumpus ahead, and there's a wumpus alive. Okay, so we're given that. Okay, so let's say that's true. Okay, based off of prior knowledge, it's true. Okay, so then we can infer that the thing to do is shoot. All right, so there's another useful inference rule, and this is called and elimination. With and elimination, you have a conjunction. If I assume that A is true, I can infer that the other thing is too, right? So let's say that I'm given A, right? I know that A is true, okay? Then if this entire thing here is true, then I must know that B is true also. If we have a sentence, wumpus ahead and wumpus alive, we can infer wumpus alive. Okay, so what these rules allow us to do, modus ponens and elimination plus those logical equivalences, combining all those things, using them all together, okay, what that allows us to do is that allows us to generate some inferences that are sound, and we won't need to enumerate models. We don't have to go through and generate a whole bunch of truth tables, okay, to be able to make our inferences. The logical equivalences can be used as inference rules themselves, okay? So let's take a look at these two examples right here, okay? One of the equivalences in that table was by conditional elimination, right? So if you're given A if and only if B, right? Then a logical equivalence is alpha, I say A, I should have said alpha, but alpha if and only if beta, then that's logically equivalent to alpha implies beta and beta implies alpha, right? If you remember how if and only if works, that's right? Because for that to be true, you know, it has to work in both directions. So alpha has to imply beta and beta has to imply alpha, right? But the reverse is true too. You can substitute alpha implies beta and beta implies alpha. If that's one of your sentences, okay, in your knowledge base, you can replace that, but with the bidirectional, okay? Now, it doesn't always work like that. It doesn't always work both ways, where you can always replace, you know, alpha if and only if beta with, you know, the implications, and then in the reverse. You can't always do it that way, but you know, often you can. So, for example, modus ponens doesn't go in both ways, right? So you can't get that A implies B and A from B, okay? So what that means is that you can't say, well, A must be true because B is. You can't, it doesn't work that way, right? You can only use modus ponens to say, well, if A is true, then I can infer B. You can't do it in the reverse. You can't say, well, if B is true, that infers A. It doesn't work for modus ponens, right? But it does work for all of the logical equivalencies. Okay, so example time. I place the table of logical equivalencies in the upper left-hand corner here just for reference. And so what we want to do using these tools is we want to prove from our previous Wampus World example, we'll prove that there's no pit in square, what was it, 1, 2, okay? And so what that means is that we're trying to prove this sentence right here. No pit in 1, 2, okay? Now, from that previous Wumpus World example, our knowledge base had these sentences in it, right? These statements of fact, right? One of them was that there was no pit in 1, 1, which makes sense because starting position, you can't have a pit, right? That's just the rule of the game. Another was if you have a breeze in square 1, 1, then that means that there has to be a pit in either or both of the adjacent squares. Okay, that was another sentence of the knowledge base. Another was if there's a breeze in 2, 1, then that means that you have to have a pit in 1, 1, or a pit in 2, 2, or a pit in 3, 1. Okay, so basic rule of the game, right? The adjacent squares have to have a pit, one or more pits. Okay, and then there was another rule here. We didn't detect a breeze in 1, 1. Okay, the sensors didn't pick it up. And another rule was, or another statement, another sentence was that there was a breeze in 2, 1 that was detected. Okay, so based off of that starting set of sentences, right, we can go through and start applying some of these logical inference rules, some of these equivalencies, to try to get to our goal, which is no pit in 1, 2. Okay, so now when you're doing proofs like this and you're going through and you're working through it, sometimes it's a lot of trial and error, right? Until you finally find the right sequence of substitutions of equivalencies that get you to your goal. Sometimes you might not be able to, right? In which case you can't prove that that's the case. But you know, it's not something where you just sit down and you just methodically get it on the first try, right? There can be a lot of trial and error. Okay, so anyway, so we're going to derive a new sentence. Okay, a new sentence. Okay, we call that R6. And this sentence is going to be derived by the biconditional elimination. By biconditional elimination. Okay, so you can see that equivalency in the table, right? Biconditional elimination. Now the alpha, the beta, and I guess that's what, theta, I think, that little T looking thing, those just represent arbitrary sentences, right? So, you know, maybe not P11 would be alpha, you know, or B11 would be alpha, okay? So by biconditional elimination, I can transform R2 or R3 into something else. Okay, so what I'm going to do is I'm going to take B11, right? I'm going to take R2 and I'm going to transform that rather than rewrite the entire thing. I'm going to do a substitution. Okay, and so the B11 would form the alpha, and then the P12 or P21 would form the beta, right? So if you look at alpha, if and only if beta, that's logically equivalent to alpha implies beta and beta implies alpha. So I can rewrite that sentence and come up with a new rule, which I'm calling, or a new sentence called R6. Sentence R2, right, this guy right here, is logically equivalent to B11 implies P12 or P21. Okay, and the reverse, P12 or P21 implies B11. Okay, so that's my first kind of substitution that I did. Okay, that's my first substitution that I did. Okay, and then I'm going to continue. Right, so now I'm going to use and elimination. And that's going to create a new sentence by and elimination. Right? So remember, and elimination was A and B can infer B or A. Okay? So by that, what we're able to do is we're able to come up with a new B or A, I should say here. We're able to come up with a new sentence, and that sentence is going to be, let's see here, R6 is going to be logically equivalent to this guy right here, right? Which is P12 or P21 implies B11. Right, so I'm doing that and elimination. A and B, right, implies A. So here's my A, here's my B, so that's going to imply, either one of these guys. I'm going to go with this one right here. Okay. All right, so that gives me a new sentence, which I'm calling R7. Okay. So I'm going to generate a new sentence. We're just going to keep on going. And this one is going to be generated by contraposition. Contraposition. Right? So take a look at contraposition up here. A implies B is logically equivalent to not B implies not A. Or, sorry, this is Greek. Alpha implies beta is logically equivalent to not beta implies not alpha. Okay? So that sentence R7, right, that is logically equivalent to me flipping that thing around. So to not B11 implying not, let's see here, P12 or P21. Okay, so because this right here is the alpha, this right here is the beta, contraposition flips their position and makes them both negative, right? So the beta became the alpha, made it negative, and then the alpha became the beta, made it negative. Okay, so that's my new sentence, R8. So I'm going to do another transformation here, another substitution, another equivalence, and this time it's going to be by Modus Ponens, and I'm going to use sentence 4 here. Okay, so remember what Modus Ponens was. This allows me to do something like, Modus Ponens is A implies B, right? Given A, you can infer B is true, right? So if A is true, you can infer B from it, okay? So what was R4? R4, we said, well, there's no reason 1-1, right? So that's going to be our given. That's the A part, okay? So that's R4, right? B1. Okay, so that's given. So that means that we can infer the sentence not P12 or P21. Right? So that's our new sentence, which we're labeling R9. Okay. So R8 is logically equivalent to not P1 R8 is logically equivalent to not P12 or P21. Okay, by Modus Ponens and using R4, right? So then, by De Morgan's rule, we're going to get a new sentence by De Morgan's. I'm just going to keep doing these transformations. That's all I'm doing. So by De Morgan's rule, right? So you can see De Morgan's up here. So not A and B or not A or B. Well, this is not A or B. By A, I mean, again, sorry, alpha or beta. By not alpha or beta, right, by De Morgan's rules, not alpha or beta, that's logically equivalent. R8 is logically equivalent by De Morgan's rule to not pit 1, 2, or not pit 2, 1. Okay? So I've gotten basically, right, or sorry, this should be R9. R9 is equivalent. Okay, so through this series of transformations, I started off with these first 5 facts, right? And then I just started applying equivalencies and inference rules. Now I've gotten to the point where I have a sentence that says there's no pit in square 1, 2, and or, this is an or here too, but there's no pit in 1, 2, or there's no pit in 2, 1. Okay, so therefore, since I was able to get here through all those transformations, therefore I can say that there's no pit in square 1, 2, or there's no pit in, that should be pit, sorry, in square 2, 1, and therefore there's no pit in square 1, 2. So what was I trying to prove? There's no pit in square 1, 2. I just proved it. Okay. Okay, so that proof example I just did for you from the text, right? That's an example of a manual proof, right? I did that by hand. But you don't have to do proofs by hand, okay? So in chapter 3, we had all of those search algorithms. You can use those. This is what's really the coolest part about the whole section to me, or the chapter really, is that you can use those search algorithms from chapter 3 to do proofs, right? So how? Well, what you have to do is you have to define a proof problem, okay? So remember all those different things that we had to spell out, you know, what was the initial state, what are the actions, result, goal, all that kind of stuff. Okay, so what you do is you set up your initial state. That's how you define it, right? That's going to be your initial database. So just like before, with that example I just did a second ago, you know, the initial database was R1, R2, R3, R4, R5, okay? Now the actions that you have to define for the problem, those are made up of the set of actions that are all of the inference rules applied to all of the sentences that are matching, you know, the top half of the first part of the rule. Okay, so actions are, you know, all of your actions that you're defining. This is the set of actions. They're all the inference rules applied to all the sentences matching the top half of the rule. Right. So what's the result of applying actions? Well, the result, the action result, is to add the sentence in the bottom half of the inference rule. Right, so top half of the inference rule, the first part of the inference rule, that's going to be your action, and the result is the bottom part. Now, what's the goal? The goal is going to be that state which contains the sentence that you need to prove. Okay, so doing searching through proofs like this, or searching for proofs, this is an alternative, right? You don't have to enumerate models. You can set up your search problem and then run any of your search algorithms from chapter 3 to find your proof. You don't have to do model enumeration. Okay, now this can be a lot more efficient. Why? Because you can ignore propositions that aren't relevant. Okay, so for example, if you needed a proof that led you to, you know, no pit in 1, 2 or no pit in 2, 1. In that previous example, did we even care about B2, 1? Did we even care about P1, 1, P2, 2, P3, 1? No, we didn't need that. The goal only existed in our sentence, which was R2, right? So all of those other propositions, right, we didn't need to worry about them. We didn't need to worry about R1, R3, R5. They didn't matter. Those other sentences didn't matter. If you remember when I was going through the proof, I only used those things that I needed. Okay? Yeah. So we could add billions and billions and billions of sentences to the keyboard, or to the knowledge base. It just doesn't matter, right? But we'd still only use those propositions, only use those sentences that we need to do the proof. Now, with the truth table algorithm, right? Remember when we were going through and examining how the truth table enumeration algorithm worked, right? Those models would be growing at an exponential rate because for every sentence that you add to the knowledge base, right, that's going to make your truth table that much more complicated. Okay, so next up I have to talk to you about this term monotonicity, right? So there's missing an I in here. I apologize for that. It should be spelled Monotonicity, monotonicity or monotonicity, however you want to pronounce it, whatever. This is just an idea. It's a name for an idea here, and that just says that hey, the set of all entailed sentences can only ever increase, can only ever grow when you're adding additional sentences to your knowledge base. Right? So the more data you have in your knowledge base, the more information that you have in your knowledge base, the more entailed sentences you're going to have, right? So, for example, if you have, any sentences alpha and beta, right? If your knowledge base entails alpha, then adding beta, right? The knowledge base that you had and the new sentence beta, that's still going to entail alpha, okay? So any knowledge that you add to your knowledge base is going to let the agent draw more conclusions, okay? You're not removing the ability to infer things or to draw conclusions. You're adding the ability to infer new conclusions, right? And you're not going to invalidate any of the other conclusions that you could have inferred from an earlier version of the knowledge base, right? It only gets better. It doesn't get worse. Inference rules themselves, they're sound, okay? But algorithms relying on them only, they're not necessarily going to be complete, right? So if you're missing one of these rules, right, the search algorithm might be unable to find the goal, right? So if the knowledge base doesn't have one of the rules, or if you can't, if it can't utilize it, then you might not be able to find the goal. You might not be able to complete your proof. So for example, if you were to remove the ability to do by conditional elimination, there, right? Our previous proof that we just went through that I showed you on the whiteboard, it would fail, right? Because the chain of conclusions included using a substitution, which was that by conditional elimination. Okay, so to get around that, to make sure that you can always find the goal, we need a new inference rule that will allow us to have a inference algorithm, or to be able to ensure that we have complete inference algorithms. Okay, and when we have that rule and we pair a inference algorithm with one of the complete search algorithms from chapter 3, then what we have is the ability to make sure that we will find our goal. Okay, so if our inference rules are adequate, we can reach the goal, and therefore we can have a proof. We can find a proof. So what we're going to need, the rule that we're going to use for that, is called resolution. All right, so time for another example. We've got our table of logical equivalencies up there, and I added next to it a picture of a scene from Wumpus World where the Wumpus moved to, excuse me, not the Wumpus, the agent moved to square 1, 2 and detected a stench, right? So it's in there, detected a stench, did not detect a breeze, so we're going to add to our knowledge base sentence R11, R11, no breeze in 1, 2. Now, if there was a breeze in 1, 2, that would imply that there'd have to be a pit in 1, 1 or 2, 2 or 1, 3. And by using the process we saw in the previous example, we can infer that there is no pit in 2.2 and that there is no pit in 1.3. So we'll add those sentences to our knowledge base as well. Now remember the sentence for R3, right, which was if there's a breeze in 2.1, then that there's only a breeze in 2.1 if and only if there are pits in adjacent squares. Okay, so if we apply to that sentence the bidirectional elimination rule, right, then that would transform that sentence into B21 implies a pit in P11 or P22 or P31, right? So there's a pit in square 1.1, or there's a pit in square 2.2, or there's a pit in square 3.3, right? That's one part of that equivalency, but also there's an and part, and that's the reverse. And there's a pit in 1.1, or there's a pit in 2.2, or there's a pit in 3.1 would imply that there has to be breeze in 2.1, okay? So if we do that and then we apply Modus Ponens, right? Modus Ponens, if we apply that using R5. Now what was R5? Let me put it here just to refresh your memory in our knowledge base. Breeze to 1. That was one of the sentences that we had. Okay, so if I take the new sentence here and I follow up with Modus Ponens and R5, okay, then what I have is something that looks like this, right? B21 implies P1 or P22, that should be P11, sorry, or P31, okay? So that's the alpha part, that's the beta part. Now we're given alpha, right? Because R5, okay, it was already in our knowledge base. Okay, so given that, we can infer P11 or P22 or P31, right? So I can add that sentence to my knowledge base. P11 or P22 or P31. Next up, I'll apply the resolution rule. We'll apply the resolution rule using R13. Okay, resolution rule with R13. Now, what was R13? No pit in 2.2, right? So I'm going to apply that resolution rule using R13 on R15. Okay, so if I do that, then I'm going to get a resolvent, okay, and the resolvent is the subsequent sentence. Okay, so what I get is a new sentence that looks like this, right? So I'm applying R13, R13 to R15, okay, and so what that gives me, the resolvent is P11 or P31. Okay, so what did I just do here? I just did a cancel. That's it. That's what the resolution rule does. It just allows you to do canceling. So because of a previous sentence in my knowledge base, there is no pit in 2.2, right? So when I derive this new sentence, R15, P11 or P22 or P31, I can create a new sentence by canceling out the P22 because of a previous sentence that was already in my knowledge base. So that gives me a new sentence, P11 or P31. So what we can say is, or if we were to translate this into English, we could say, well, if there's a pit in 1.1, 2.2, or 3.1, and I know previously that there's no pit in 2.2, then it has to be in 1.1 or 3.1. Now, similarly, we can apply that resolution rule again using, one of the first rules that we had was that there's no pit in 1-1 because it's the starting square. So if I apply the resolution rule with R1 onto R15, that will get me yet another sentence, right? The not P11 and the P11 are going to cancel. So that's going to leave me with a sentence P31. Okay, so similar language, if there's a pit in P11 or there's a pit in 3-1, and I know that there is no pit in 1-1 because of sentence R1, then it must be that the pit is in 3-1. Okay, so this is an example, or these were examples of what's called the unit resolution inference rule. Okay, the unit resolution inference rule. We can cancel. Okay, if we have a sentence and there's a previous sentence that negates it, we can cancel and make a new sentence. Okay, so those last two steps, they were the example of the unit resolution inference rule. Here's a summation of what that rule is, right? So you take a look at this top line right here, and this just says, look, I got a literal, right, a series of literals that are connected by disjunctions. You got literal 1 or literal 2 or literal 3 or literal 4 or literal 5 ... or literal k, right? And then I have some other literal m that's complementary to one of the literals in that list, right? So if that's the case, then what I can do is I can cancel them out. And so what this underneath the line is showing us is that, look, there's a gap now, right? So where before it was L1 up through LK, the M canceled out, right? One of those, right? It canceled out the ith literal. So what you're left with is literal 1 through literal I minus 1, and then you continue on with literal I plus 1 through K. Okay, so we can generalize it even further. And this looks really crazy too, right? But all this is saying is, look, if you've got a disjunction of literals, L1 through LK, and you have another disjunction of literals that are complementary, M1 through Mn, then the entire sequence will cancel, right? So, and give you, a new sentence that, takes that cancellation into consideration, right? So this is just saying, all right, cool, well, literal 1 up through literal I minus 1, and then literal I plus 1, keep on going up through K, right? So all of the things that were canceled were in between literal I minus 1 and literal I plus 1. But you can have, this other series of literals that were complementary, right? Maybe not all of them were complementary. So when it's finished, you end up with, what's left over. So take one set of literals, disjunctive literals, take another set of disjunctive literals, apply them to each other, and then you get a brand new sentence with the complements canceled out. So it sounds really, really, really complicated, but here's an example, right? So let's say that we've got, two disjunct clauses or two disjunct sentences, P11 or P31, and we have a second one, not P11 or not P22. According to the cancellation that happens, according to the full resolution rule, what's going to happen is you try to combine these two things together. Well, the P11 cancels out P11 and not P11. They eliminate each other. So what you're left with is a new clause that is the remnants of the first disjunct and the remnants of the second disjunct to give you your new clause, P31 or not P22. Okay? Now, resulting clauses, they should only have, and I keep saying sentences and clauses. Let me clarify really quick, right? So a clause is a sentence that has nothing but disjuncts in it. right? So A or B or C or D or E, that's a clause, okay? So a clause is also a sentence because it's just a sentence that has disjuncts, A or B or C or D or E, right? So this is P31 or not P22. That's a sentence, but it's also the resulting clause of combining these two clauses above the line together. They canceled out, and then here's what you have is your new clause here. And you should only have one copy of each literal, right? So if you have duplicates, then you're going to remove those multiple copies, and that's perfectly valid, it's perfectly legal. You're not going to break any of the logical equivalency. The logic's not going to break. And so removing those duplicates, that's called factoring. So for example, A or B resolved with A or not B. If you combine those two clauses together, what you would get is A or A, right? Because the B and the not B cancels. And so A or A, well, that's, you can get rid of one of the extra A's, because if A is true, the whole thing's true no matter what, A or A. I mean, you can cancel out the extra one, and that's just going to give you A. That's what's left. Now that resolution rule, it's only going to work for clauses. It's designed, it's built, that's how it works. Logically speaking, it's only going to work for clauses. Okay. Now that resolution rule, it allows us to have a bunch of complete inference procedures, okay? And we'll see how those things work in following sections, okay? All right. Okay, so next thing up I want to talk to you about, or I need to talk to you about, is conjunctive normal form, okay? And what this does is it allows you to use the resolution rule for any kind of sentence, right? So with some pre-flight work you have to do, right? Because the resolution rule will only work for clauses, okay? It only works for clauses. But that doesn't mean that you can't still use it or take advantage of it, okay? You can make it work, in an inference procedure, in an inference algorithm, for any propositional logic, for any sentence, so long as you do something first, so long as you do some pre-flight work. And that is that in your knowledge base, each one of those sentences gets converted to what's known as conjunctive normal form. Okay? So all propositional logic can make use of the resolution rule so long as you convert the sentence to conjunctive normal form first. All right, so example time again. So let's say that we have a sentence, so let's say we have a sentence that looks like this, right? So let's say that we've got B11, which we're going to use a bidirectional, which is going to imply there's a pit in 1, 2, or there's a pit in 2, 1, right? So if you got a breeze in 1, 1, that means that there's got to be a pit in one of these other squares, or one of these adjacent squares, or both of them. Okay, so I want to convert this. This is not in conjunctive normal form. Okay, so CNF looks something like this. Right, so there's one clause. Okay. Here's another clause. Okay. And here's another clause. That's conjunctive normal form. Okay. So this sentence right here, not conjunctive normal form. Okay. So in order to make use of that resolution rule, we got to be in conjunctive normal form. Okay. So first thing we're going to do is we're going to start applying some of these logical equivalencies to get it into the right form. So we can start off by doing biconditional elimination. And so if we do biconditional elimination, right, then that will transform that sentence, or we can get a new sentence, maybe I should say that. That looks like this. Right? P12 or P21. Okay. And P12 or P21 implies B11. Okay, cool. Now, another transformation I'll do will be by implication elimination, right? So that one right there. Okay, so once I've applied that, then what I end up with is this new sentence that looks like this, B11 or P12 or P21 and not B12 or P21 or B11, right? And so that was by implication elimination. So implication elimination says, look, you can take the implication alpha implies beta, and it's logically equivalent to not alpha or beta, right? And so then I just applied that to both of these clauses and got my new sentence, okay? And I say both these clauses, but I mean both of these, because they're not clauses, right? To both of these sentences, okay? Both of these parts of the sentence, okay? So once I've done implication elimination, I have this form. Now, conjunctive normal form requires that you only have negation on the literals themselves, right? So something like that, okay? So what we need to do is we need to move, right, this negation. It's in the wrong place, right? It's negating a disjunction, and I need it to be negating literals, okay? So what you can do is you can move the negation inwards by repeatedly using double negation elimination in De Morgan's, right? So what does De Morgan's do, right? We'll take a look at this first rule right here. We'll take a look at both of them, right? So there's a negation on the outside of the disjunction here, and its logical equivalent, not alpha or beta, is logical equivalent to not alpha and not beta, right? So we can apply De Morgan's rule, okay, to get us something that looks like this, not B11 or P12 or P21, right? And so that's going to be applied. That's going to be applied just on the second part here, okay? So by De Morgan's, we can say, all right, well, then this is going to become not B12 and not P21, right? Or B11. Okay, so we're getting closer, right? Now, we'll finish it off by applying one more equivalency, and that's going to be by the distributivity laws, right? So these guys right here, okay? So you can scan over those as I write this out. So that'll give me a new sentence, not B11 or P12 or P21 and not P12 or B11 and not P21 or B11. Okay, so once we've made that final transformation or application of the distributivity laws, then we end up with something that is actually in conjunctive normal form, right? So this is in CNF, okay? So there's one clause, there's another clause, there's another clause, and they're all linked together with ands, and the nots are all in the right place. The negations are all in the right place, okay? So again, this is required so that way we can then use the resolution rules on these clauses, okay? And by being able to use the resolution rule on these clauses, we then can guarantee that inference algorithms are going to be sound when they get paired with sound search algorithms, Okay, so that guarantees that you're not going to have any problem with finding a goal if it exists. Okay, so it's a need, it's necessary. Okay, so let me just summarize a couple, because we threw some terms at you. So that original sentence, this one right here, has been converted to conjunctive normal form, to CNF. Okay, now let me just throw some notes at you here. So CNF is a conjunction of clauses. Okay, what's a clause? A clause is a disjunction of literals. Okay, so here's a disjunction of literals. Here's a couple examples, right? So if I've got literal, call it L1 or L2, right? That is a disjunction of literals. Disjunction is or. Another example, L3 or L4, right? So there's a literal, there's a literal, there's a literal, there's a literal, and they're linked together by ors, right? So conjunction is and, disjunction is or. CNF, conjunctive normal form, it's a conjunction of clauses. So these two clauses, if we were then to link them together with an and, this would be a conjunction of clauses. Remember, a clause is a disjunction of literals. Okay, so this is in CNF form. Okay, so now that we've set all that stuff up, okay, we've gone through all of that. Now it's time for the payoff, right? Let's go through and look at a resolution algorithm. A resolution algorithm is going to use proof by contradiction. Remember way back when we were talking about proof by contradiction? So the payoff is we want to show that a knowledge base can entail A, right? So in order to do that, we're going to do proof by contradiction. We'll show that, adding not A to the knowledge base. So knowledge base and not A is impossible. So here's how the algorithm generally works, right? And this is going to be sound and it's going to be complete. That was the whole point for having, CNF. That was the whole point for introducing the resolution rule. All the work that we did up to this point was so we could have a resolution algorithm that was sound and complete. So here's how this algorithm generally works. First thing you have to do is you have to convert your knowledge base and the not A, right? The opposite of what you're trying to see is entailed to conjunctive normal form. So you take your knowledge base, and that knowledge base, now there's something to remember, right? So far we've been showing the knowledge base as a series of sentences, right? But you can tie all of those sentences together with a giant series of ands. You can make a giant conjunction out of them, right? Sentence 1 and sentence 2 and sentence 3 and sentence 4 and sentence 5. That makes up your entire knowledge base, okay? So we can take that sentence and the negation of whatever sentence we're trying to see if the knowledge base entails. We'll take that and then we'll convert that to conjunctive normal form. Once you've done that, the next step is to apply the resolution rule to each of the individual clauses. I'm going to show you an example of this too. Or each pair that's containing complementary literals resolves. Okay, so you pair up clauses, and every pair that contains complementary literals, they resolve, right? So you do that elimination, so that way you can create a new clause. Now each new clause gets added to the set, right, to the set of clauses that were the result of the first conversion, if it's not already there. Okay, now you repeat all of those steps, okay, applying the resolution rule to the clauses, resolving the complementary literals, adding the new clauses if it's not already there. You keep doing that until no new clauses can be added. And that means, if that's the case, if you get to the point where you can't add any new clauses to your set of clauses, that means that your knowledge base is not able to entail your sentence A. Okay. The other thing that's going to stop this loop is if two clauses resolve to the empty clause, right? So if everything eliminates everything else and you end up with nothing in a clause, then your knowledge base does entail your sentence A. So what's an empty clause? It's a disjunction of no disjuncts, right? So, it's nothing and nothing, right? And that would be the result of A and not A, right? They would, or A or not A, excuse me. They would eliminate each other and you'd have nothing left in that clause. Okay, so this is going to equal false because a disjunction is going to be true only if at least one of the disjuncts is true. So if there's nothing there to be true, then the thing's going to be false, right? And so if it's false, then that means that your knowledge base and not the sentence, right, is false. There's your contradiction. Okay, therefore, the knowledge base must entail the sentence that you're trying to determine if it entails, right? So we're trying to show that the knowledge base and the negation of the sentence is impossible, right? And so if you end up with that empty clause, then that means that this is not possible. And if that's not possible, it means that A is entailed by your knowledge base. Okay, so let's look at an example of that algorithm in action, right? So let's assume that we have the agent in square 1, and he detects no breeze. Let's look at a relevant knowledge base. That would include sentence R2 and R4. In sentence R2 from our knowledge base was if there is a breeze in 1, there's only a breeze there if and only if there's a pit in either square 1, 2, or there's a pit in square 2, 1, right? So that's the first rule, the first sentence. The second sentence was, well, there's no breeze in 1, 1. So that's the R4 part. So combine them together and you get a knowledge base, a relevant knowledge base that is consisting of this conjunction, right? So sentence R2 and sentence R4. Now what we want to prove is that there's no pit in square 1, 2. That's what we're trying to prove using this inference procedure, using the resolution rule. And remember, this is done by trying to prove that there's no pit 1, 2 by contradiction. So that means that we want to see if our knowledge base is going to entail our sentence alpha. In this case, the sentence alpha is no pit in 1, 2. So what we do is we start off by converting knowledge base and the opposite of that, the negation of what we're trying to prove. We're going to try to prove that this is impossible. Okay, so you convert that to conjunctive normal form first, according to this algorithm, and then you end up with this first row here, right? So this is the first clause, okay? This would be the second clause, right? This would be the third clause, this would be the fourth, and this would be the fifth, okay? Now, the algorithm then states, start pairing off those clauses and apply the unit resolution rule, eliminating literals as you go. And as you're applying that resolution rule, you end up with new clauses. And you just keep doing it over and over and over again until you end up with an empty clause. Or there's no more clauses to add to your set. So without going through every single one of these, I think I can just go through a couple to give you an idea. If you paired off this guy right here along with this guy right here, then what you end up with is a new clause, this guy right here. So pair off A and B and you get clause C. And what did we eliminate in that case? We eliminated the B11 and the not B11 in our new clause, right? So you do that, and then if you pair off this guy and this guy, right? So in that case, you're eliminating the B11 and the not B11, and that leaves you with not P12, right? And so you're just doing that over and over and over again. So this second row is all of the new clauses that were generated from pairing off the initial CNF. Okay. Now eventually we get to a point where we can pair off not P12 and P12, right? So when you pair them off, right, not P12 and P12, okay, these guys can eliminate each other because of the unit resolution rule. And so what that leaves you with, once you paired them off, okay, is that empty clause. Okay, and since there is no literal in there to evaluate the true, then that means that that thing is going to evaluate the false. So what does that mean? That means then that it is false to say that our knowledge base and not our sentence is true. So this then is false. So that's a contradiction, right? So since this is false, it must mean that this is true, right? That the opposite is true. That is to say that our knowledge base entails the sentence we're trying to prove, which is not P12, okay? So since it's impossible for us to combine, for us to have our knowledge base and the negation of our sentence, right? It's impossible to have our knowledge base and pit in square 1, 2. Therefore, our knowledge base informs us that there is no pit in square 1, 2.